Okay, so let's start. Uh, I will try to go through that like pretty fast. So in we have how much of subchapters we have? Like 12. Yeah, a lot of subchapters here. So basically, the first one was about the like U and R processes. So U is kind of the continuous evolution of quantum system governed by the Schrodinger equation, and R is kind of the discontinuous collapse of the wave function, which kind of interrupts the Schrodinger evolution, collapses it to some state, um, something like that. So that's basically it.
Are you
And
sharing your notes, Slaven?
uh,
Sorry to interrupt. We see a page, the cogsci.uci.
probably I shared with you like the wrong browser screen. One moment.
Now we see your notes.
Yeah, sorry. I just missed because like two windows had chapter 22 summary opened previously. Okay, so yeah, so the first subchapter was about UNR processes, as I have told you, and uh, afterwards we talked about the linearity of the U process there and the unitarity of it in the next subchapter. Uh, and basically that's like about the the first one is about linearity. Basically, if we have like two solutions, then the linear combination will also be solution for the Schrodinger equation. Um, but even the linear nature of the process will already kind of make some conflict with the R process. Uh, don't remember the exact place where he was talking about that, but okay. Anyway, yeah. Here also he said that if we want to think that U is the whole story, we need to use many worlds theory, uh, and we'll talk about that also later, somewhere in the later chapters. Yeah, and Penrose's point here is that many worlds view is just a result of believing only in the U process and kind of automatic entanglement while observing the systems. Uh, yeah, we have some new noisy member here. Joe, happy mask sales. Hello.
Oh, sorry. Yeah, hello. I'm a bit loud on the keyboard.
Yeah, yeah, it's okay, it's okay. Just wanted to say, yeah, please mute. Okay. So, and we talked about unitarity for the U, and basically it's like a norm preservation. Um, mhm. We talked about direct notation, like bra and cats, and sandwiching the linear operators inside that, and like taking duals there. Okay, and talked a little bit about unitary evolution, Heisenberg picture, uh, which is kind of dual one to the Schrodinger picture, and there we have like uh, the static wave function and our observables, they are changing in time instead. Okay, let's stop there for a moment. So basically it's like one sort of the chapter 22. uh, Maybe you had some questions about the that first part of the chapter.
So I had one question here, and that's how is matrix mechanics different from integral mechanics? So like you can like as we did in I think 21, you can write a lot of these things as just like integrals over all of space, right? You integrate the wave function, you should get one. How is this different in matrix mechanics?
Like, will we have the same integrals but with matrices inside or something?
Right. Yeah, so like I guess I'm just asking like why is the Dirac notation useful here? Because you could just do the integrals and you get similar results.
Yeah, it seems to me like a hard question to answer actually. Yeah, so maybe we can Google something about that. Let's try.
I mean, I have a speculation, and it's that if you already know the eigenvalues or like you know the possible values that could be measured, then you can actually work in a discrete space rather than a continuous space. That's just a guess. I mean, sort of a secondary idea to that is like, usually when we do these integrals, they're either in like position or momentum space. And position and momentum are continuously varying, but something like energy is more discretely varying. So perhaps the matrix mechanics are better for these discrete eigenvalues.
My intuition here is that like when you move from the wave function picture to the matrix-like picture with those dynamic variables, things and stuff, then you kind of moving from like the direct values to the questions about those values, right? And you will have like dynamical questions. So basically those matrices changing in time is like asking some question about system in time. So it's kind of the dynamical question asked. And therefore you will have like change in those eigenvalues. So those eigenvalues, they will be discrete as functions. So at each time they will be like a discrete number of things to be measured of, I think, but they will be continuous in that matrix semantics or language or approach, because like they will change instead of the wave functions. I think something like that. So basically you kind of shifting from dynamically evolving state and fixed measurement things to dynamically changing questions about the system. Something like that, but it's kind of my intuition behind those.
Okay, I have one follow-up question with that is how do you form the matrix operators? Like, say we have a Hamiltonian, and like say we're starting just from the classical Hamiltonian, where you have like p squared over 2m plus v, where v is the potential. How do you end up with a matrix from that?
Yeah, that's interesting question. That's interesting question. Yeah, for some reason I don't know why, but it's pretty hard to find that Heisenberg theory in Google. Maybe it should be called with some other thing like matrix notation in quantum mechanics or something. Matrix mechanics. Oh, matrix mechanics. Okay, so it seems that that's it. That's it.
Oh, and the first thing there is the Epiphany at Helgoland.
Yeah.
Not just a fever dream.
Hmm. So, see, he got there some kind of revelation about non-commuting observables while thinking about poems from Goethe's book.
So I have a guess as to how to form a matrix operator, and I think it's kind of from linear algebra. You know, like a good visualization is like the 3 blue 1 brown essence of linear algebra stuff, where a transformation matrix, the columns of it are dot products of like the basis vectors before the transformation and the basis vectors after the transformation. And that sort of like forms the columns of a transformation matrix.
Mm-hmm, mm-hmm.
So I think that these matrix operators are basically projections from the initial basis to the final basis. Like each component would be like taking the first, the top left component would be like taking the first basis vector in the initial basis and projecting it onto the first basis vector in the final basis.
You can see here actually that like Hamiltonian in that case is like some kind of combination of P and X matrices, and P and X matrices, they are probably the matrices built up on the energy here, and energy is calculated by using some kind of the, like Planck's formula and constants here. I'm not sure what reconstruction here means. Reconstruction is 0.
Well, so like for example, just the basic linear algebra case. Say you have a vector in R2, and you want to rotate it. Well, the matrix that you end up with, the first column is like cosine theta, sine theta, right? And that's where the unit vector in the x direction, that's where it lands after rotating by theta. So I think that's like an inner product, or well, I suppose it's maybe not an inner product because we still end up with a vector. So
yeah, like, but if
I'm just wondering about the components of that matrix. How do we get the components?
If you take a look at some formulas from chapter 22, I think we will get only matrices there, right? So there will be no wave functions or vectors for those to act upon. Almost there. One moment. Sorry, too much. Yeah, so here's the analogous like evolution equation but for the Heisenberg evolution picture. So all we will have here is just like matrices, and like those operators. So, and it seems to me that those matrices, they like do not act on anything actually here, like in obvious way. So they will act, but they will act probably on that static state, like wave function state of a system. But yeah, that's kind of hard to think now, because uh, like for me, like with that old presentation from the Penrose book, that Heisenberg picture seems like a hack. So from his perspective, because we kind of just redefining our wave function to be constant using the unitarity condition here, and just like applying u minus 1 t to the Schrodinger wave function here and obtaining those Heisenberg wave function things here. So it's kind of really hacky way to say that everything is in that picture kind of stable for the wave functions, and putting all the dynamics into the observables. Um, so basically those components in matrices will mean the same thing which they mean in the Schrodinger picture uh, for observables. And if we will think about observables, then observables matrices, um, they will probably give us like the thing you've been talking about, right? Like going between different bases, and uh, basically they are all about the amplitudes, about passing from like state I to some other state J, right? So I think that Heisenberg picture is just moving the change or evolution inside those amplitudes and making those observable matrices like dynamic. And those components are just like probability amplitudes from like jumping from one state to another basically, and that's it. You've been trying to say the same, Joe, right? About the basis things.
Yeah, I think so. I was thinking like, for these simple like finite dimensional systems, like a spin half or something. We have two dimensions. So the operators would be 4 by 4 or 2 by 2.
Mm-hmm.
And so I'm just wondering like, what are the diagonal components of those matrices, or what are the off diagonal components? Because it seems interesting, because like we talk about these operators just kind of abstractly. We don't explicitly list out the components. So I was just wondering if Penrose goes into like how to actually get the components. But I think I think we're in agreement here. It's about the projection from the initial basis to the final basis.
Yeah, and it seems to me that like every such observable, it will have like a set of eigenstates fixed, and you can kind of measure the components statistically by experiment or something. So you will know that you can have like n outcomes at the end, and you can observe statistically the amplitudes of probabilities and somehow calculate those for the current measurement device. So I think that it's done something like that. So, but it's just like my intuition here.
Yeah, I agree. If you have like if you have an equally of it, and you look at the outcome from a measurement on each copy of that system, then you can like build up the whole distribution.
Yeah, but that's an interesting question actually, and basically I think that actually what we need to Google here is like how to calculate or something. Calculate the quantum mechanical observable or something. Quantum mechanics observable matrix. Okay, seems too theoretical for me. Maybe here, just in Wikipedia.
I think. Oh yeah, let's check Wikipedia. I think I saw something in there that might be pretty relevant for us.
Yeah, it seems that they just do not talk much about how to calculate those.
Well, so can we go back to that first link that you clicked on? They had like it kind of flew by, but it looked like they had a spin matrix in there.
Let's take a look.
Yeah, it was just there. Okay, there are the components.
So it's okay. So we have like it seems that it's just like poly matrices, right? For the component. And that's how we calculate it. So basically we have that plus and minus basis.
Yeah, so this is the case. Like this would be a rotation by I pi or something. I don't know, but yeah, because the first component in SZ here is like where you go from the plus state, you measure SZ, and then you end up in the plus state. And then the component below it is you start in the plus state, you measure SZ, and you end up in the minus state. And it looks like there's no projection there. So I think it is like the linear algebra case where you just take the initial basis and then project it onto the final basis.
Yeah, so basically here we're just projecting plus and plus, and we have like just one here, right? And but we are doing that like by fixing that z direction. So basically if we project minus and minus, we will have minus 1 because we are fixed like z direction.
Yeah, and I think minus is the eigenvalue for SZ acting on minus.
Yeah, so I think that's kind of the answer here. And like those components, they will depend on the basis we will use actually. And those bases are actually the states or like resulting states after the measurement.
So it looks like the diagonal is looking at like what component of the final state is in the same direction as the state. Right? That seems to form the diagonal. And then like the off diagonal looks like transitions between states.
Yeah, so we can take a look at the poly matrices from Penrose's book here. Like for another set of components where we have like off diagonal ones and 0 on diagonal.
Yeah, so if we look at L1, it looks like it'll take a spin up and flip it to a spin down.
Yeah, seems so, but why? but why? So if you have like spin up state and we will measure it along the x-axis, right?
Yeah, so it's spin up along z. And if we measure the angular momentum around x, that'll flip the spin along z. And then the second column there is if we're in a spin down z state and we measure the x angular momentum, it'll flip it to a spin up z state. And it looks like if we measure y, it's the same thing, but we end up with another factor of I, although the sign is flipped as well. So I'm not sure.
Yeah, I think that like they are just so if you think about the eigenstates for that matrix, they will be the like vectors lying on x line, and they will be like balanced between up and down states, right? So it's basically talking about x basis for spin, like left right, in terms of plus and minus along the z axis.
So it looks like a vector that would remain unchanged is like a 1, 1.
Yeah, yeah.
And also 1, -1.
Or -1, -1.
Well, we should only have 2 eigenvectors for these because we got 2 by 2 matrices.
Yeah, yeah, that's true. That's true.
I mean, our 1, 1 and -1, -1 are parallel, so they're sort of like the same.
Yeah, 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 yeah.
Okay, I think this answers my question. Yeah, I was just interested in like actually how we form the components, and it looks like it's from that paper that we just looked at. It looks like each of the components is like an expectation value or like a projection from initial state onto final state, given that you make the measurement.
But from the explanation that Penrose wrote about these polymatrices, it sounds like the polymatrices, the component themselves doesn't have a meaning, but just because such matrices would give the commutation relation. So in the next paragraph, the next page, yes, the first paragraph, they provide the simplest representation of the angular momentum. So I suppose what he means is that there are other ways to write these matrices, is just that these are the simplest cases. So
he just talking that we can have like different representation for our quantum states and our observables. And this one is like the simplest one, like two-dimensional. But we can move to the next dimensions by using more, like greater J values, basically, for the Casimir operator.
Do you mean he's talking about the spin 1/2 being the simplest case instead of?
Yeah, yeah.
I don't know. I read it differently.
Yeah. So.
Well, I think I get your point, Yuri. It's that rather than thinking about like specifically what it's doing to each individual state, this is just the set of matrices that gives us the algebra that we observe. Is that right?
Because I think that matrix are like we assign numbers, but what it actually wanted to tell us is the commutation relations.
I think that's also true, like because in linear algebra, components do not mean much without the basis. So those components will always depend on the basis we are taking a look at. And I think that for the particular values for L operators, we are using probably the like Z basis, like up-down basis. And that's why the components has the particular form here. So if we'll switch to another basis like left-right, then probably we'll have different numbers here, and the diagonal elements will appear here and disappear from L3, for example. So we can have yet like different components when switching bases in our space of operators or wave functions.
Yeah. So then what should remain in this transition of component then is the commutation relation that
yeah so that's at the core. Yeah. Okay, so let's go back to the summary and continue. So basically in the next subchapter we were talking about the observables, and that usually they are required to be Hermitian operators with the property q star equals q, but Penrose also allows those to be just normal operators with the next property, and all he wants to be guaranteed here is that they will have like all of eigenstates orthogonal one to each other and like spanning the whole space H for our wave functions here. Yeah, and afterwards he talked about probabilities more, that for normalized states the probability to go from probably to phi state from psi is just that modulus of the scalar product squared. Yeah, and one more equation was given for the non-normalized ones, but we can just pretend that those are normalized always. And actually, if you sandwich in here the q operator, then you will see the components of q basically for different basis vectors. So if you substitute instead of phi and psi here some ei and ej vectors, then the orthonormal basis will give you the components. And basically that was the statement we talked about like 5 minutes ago with Joe, that the components of q operator of observable is just telling us the probabilities of going from ei to ej state in some fixed orthonormal basis for the wave function space.
Yeah, and I think the way to read that that probability thing that was it's just a little bit up. Yeah, I think the way that you read that is the probability to get phi given psi.
Yeah, that's it. Yeah. So just to transition from psi to phi. Yeah. Yeah, and basically using that orthonormal basis fixed, we can represent any wave function as the superposition of those things. And what was interesting in this subchapter was the note about the like momentum and position states we have seen in chapter 21. And we've seen that wave function will be described as integrals for those. And the problem here is that they do not technically form a basis, because they doesn't even belong to the normalized states. They are non-normalizable. And Penrose here just said that he just tries to steer a middle path between those things to be like a mathematical rigid guy and to have a general sloppiness in ideas. And that's kind of life, and we need to to live somehow with that. And that's like the quantum mechanical style of doing things basically. So yeah, and afterwards we talked about yes and no measurements, projectors, and basically it's just the simplest kind of the operators to have, observables, which are just asking the yes or no question about the system. The problem with those is that in dimensions, in higher dimensions, these are degenerate ones, and we will have like multidimensional eigenspaces for those, And therefore, like to determine where we will project our wave function, we need to use the projection postulate, which says that the wave function subjected to measurement is always projected orthogonally by it to the corresponding eigenspace of the observable. And here we have like decomposition for two subspaces for the projector operator E. Basically for one space is E and for other is I minus E. And that's how it looks like geometrically. So we have a function in space H, and for no answer we project it orthogonally to I minus E subspace, and for the yes measurement to the yes subspace.
And the length of each yes or no line corresponds to the probability of each. Is that correct?
Yeah. So the length of the projection will correspond to those like amplitudes, and you will probably need to square those, I assume.
Yeah, I think the length is the square root of the probability, so you could have a complex length.
Yeah.
So it looks like they're if you sum up all of the projectors, you should end up with the identity.
Yeah, that's it. So basically there are just like two parts which constitute the whole space. So you will not have anything between those. So the whole space H is consists of two parts, one belonging to the E operator and the other one to I minus E. And those two vectors are orthogonal to each other, or subspaces basically. They're kind of independent. Yeah, and in the next subchapter we talked about null measurements and helicity, where by not detecting something like the tau wave packet here, we are collapsing the wave function to zero state. And to make that happen, we need to think that those like sources and detectors are perfect ones, like perfect emitting things and perfect measurement things, to be sure that we haven't measured something basically. Yeah, we have had that experiment with the bomb here, where we can detect the presence of detector C in the way of the wave packet here by kind of non-measuring that part will collapse the wave function, and that will break the interference thing happening at the mirror at the end here near the B and A detectors. So in the case C will not measure this part of the wave function, the interference will collapse and we will have 1/2 probability of a wave function or like photon going on to the B detector, instead of previously always going only to the A detector here. Yeah, and we talked a little bit about helicity and spin here, that it could be right-handed or left-handed, and that general spin can be any superposition of those two basis states. Yeah, and we just talked about that to consider the case of the previous experiment where helicity after the reflection will switch to minus here, and therefore we will need the projection postulate to be used here to be sure that the overall wave function, that psi plus, which equals tau plus and rho minus here, will collapse to the rho minus space instead of some combination between rho minus and rho plus in the eigen subspace of our wave function space here. Yeah, so basically it's kind of proving that we need the projection postulate to be sure that this kind of wave function will collapse to rho minus and only it. Yeah, so let's stop here for a moment. Maybe some questions about those subchapters. Okay, so let's continue then. Um, yeah, and in the next few subchapters, we've been talking more about spin, and basically that we have seen that time translations gives us energy conservation, space translations give us momentum conservation, and in the same way we will have like that rotation give us angular momentum conservation, and we can kind of derive the Lie algebra for the rotation group of the space and have those poly matrices there representing the overall situation. Yeah, I forgot to finish the notes here. So basically, we were talking afterwards about the Casimir operators and like J and M values for those. Yeah, so we had that Casimir operator there and corresponding J value for the eigenvalues for it. And we formed a complete set of commuting operators for our space by adding to it L3 operator, and after doing that we were able to number our eigenstates or states of our system for the angular momentum by using two quantum numbers m and j, and m was lying between minus j and j here. Yeah, and in the few next subchapters we talked about Romanian Sphere for the two-state system, that in the case of spin 1/2 a particle, like probably the simplest case here for spin, we will have Riemannian sphere representing it, and every direction on that sphere will just correspond to the real space direction, like direction in space, and we can get by this stereographic projection the number u, which will be equal to the ratio between the amplitudes, those w and v things here. Yeah, and for different two states, like to the left and to the right, we will have the next picture for the probabilities with the cosines of theta for like with a plus for the positive projection basically, and with a minus here for the negative one. Yeah, and we also talked about the polarization there, about plane polarization and circular one, and the general case of the elliptic polarization there, and that we can determine the ellipse of polarization for a wave by using the Stokes vector scheme here depicted here on the picture. Yeah, and afterwards we went to the higher spin things, and we can take a look or like recall from the 22.8 that for higher dimensional representation for spin, we will have n-spin tensors, which are just those like spinor things with more indices here, where the number of indices will correspond to the spin n over 2 particle. And for those more general states, we will need to have the Majorana picture, and we have a theorem that we can decompose those in terms of symmetricized one index spinors, and those will be just kind of corresponding to spin 1/2 case, and therefore we can still use the Romanian sphere, but we will now have n directions in space corresponding to that like more complicated n over 2 spin particle. Yeah, and for that state, like what are those directions? Those directions just correspond for the Stern-Gerlach apparatus measurements, for which we will have zero probability of obtaining the like other direction for the measurement for the like Stern and Gerlach measurement done in that direction. Yeah, and at the end of that subchapter, Penrose said that this representation in general isn't very familiar for the most physicists, so they use spherical harmonics instead. And basically, those spherical harmonics are just oscillation of a soap bubble or a sphere. And to classify those, we need to introduce the Laplacian operator on a sphere, which looks like that. So you need to calculate the matrix on a sphere, obtain the Laplacian there, and then stick it up into the like to act on some kind of the eigenfunction there, and those eigenfunctions will be spherical harmonics, and they will have those eigenvalues really similar to the Casimir operator, and for the spherical coordinates for d phi here, they will have eigenvalues Im, and therefore we can kind of obtain the correspondence between Casimir operators and L3 operator here. Yeah, but those like spherical harmonic things will only work for the integral spin, and for half odd cases we will need spin-weighted spherical harmonics, and we will need those spinorial tangent vectors here with a flag or something. Yeah, and Penrose was kind of giving the correspondence here to the S3 and Clifford bundle and those things. Yeah, and basically the last, like, that subchapter was kind of just discussing those more general spherical harmonics till the end. Okay, so maybe any questions about that part, about spin, about spherical harmonics, etc.?
Well, I wanted to make a note because, I mentioned at the beginning of the call that I don't understand the Riemann sphere picture so well. I got the geometry of that one figure where it's like you have some point on the Riemann sphere and you can project it either sort of forward or backward, and so you'll have one minus cosine theta and one plus cosine theta. One more figure up, I believe. Yeah, here. So I get the geometry here, but I'm interested in learning a little bit more about how it would work for the higher spin picture. I posted a link in the beta chat of the way that these things are calculated using spherical harmonics. So this is a big table, but the way to read it is basically like the rows are states with like a certain projection along z for like two particles, or if you're trying to add like the angular momentum and spin of a particle, and the columns are like a total spin or total angular momentum basis. You can see that in the top right where they have M1 and M2 in the rows. So those are like the z components of either angular momentum or spin, or it could be spin of two particles. And then the columns here are the total angular momentum states, because they don't add like directly. And so what we see, all these y's that are listed in the middle, these are the spherical harmonics. And so if we scroll down a little bit, they have a list of these d functions. And okay, so up just a bit more, there's one on the right where it's d11. So this one. This is this is what we had in the Riemann sphere picture, right? 1/2 times 1 plus cosine theta. And then so there's d1 minus 1 as well, and that was the sort of complement to this this projection. So yeah, I just wanted to make a little comment about like this is how it's calculated for the most part, and Penrose makes this point about how it's all done using spherical harmonics rather than this Majorana representation. So yeah, this is how it ends up usually being done. Like this, you can write out the probability for certain processes as like the square of these d functions.
So those like small capital M's here, they correspond to the M values, right? For two different particles.
Right.
And capital J and capital M, what are those? Like total spin and
Yeah, and then z component of the total spin.
and Z component.
So
Okay.
we could look at a simple example. The leftmost table there. This is for two spin half particles, and so if both spins are up along z, then that's like having a total spin of 1 along z. But then you can see on the next row down, if the spins are opposite each other, then it's like we have a total j of 1, but the z projection of that j is 0. When what we see in the gray boxes are these coefficients. So like the way to write this out is if you have like a plus state and a minus state,
And
then this is like a
superposition.
Yeah, it's like a superposition of these states forms the 0 state, and the coefficient for these for this superposition is 1 over root 2, and that's in that note where they say a square root sign is to be understood over every coefficient. So where we see 1/2, they really mean 1 over root 2.
So everywhere we have that square root.
Yeah, and where there's a minus sign, the minus sign is outside the square root. But so this is a big table of like all the combinations that you normally run into. I mean, and even some combinations that you don't normally run into, like where's a spin half particle, or I'm sorry, a spin 2 particle. But most common is you have 2 spin halves, or you could have a spin 1 and a spin half. Those are kind of the most common tables. And from these, you can build up these superposition states that are like total angular momentum states. And from that, you end up calculating this like 1 plus cosine theta or 1 minus cosine theta. These are the d functions. So I just wanted to make a note of this because I was a little blown away seeing it in the Riemann sphere picture. You end up with the same results. And it seems a lot simpler to think about it in geometry rather than this, this is linear algebra plus, a little bit of differential equations, because that's how you end up with the spherical harmonics.
Like the Legendre equation we talked about previously, yeah?
Right, and that's what gives us these YLM functions.
So y functions come from the differential equation solutions.
Yeah, and then the d functions come from doing like integrals over these. Yeah, you can project onto particular d functions here. So on the left hand side, they're showing like the symmetry or anti-symmetry of these things. And for the most part, all I end up using from this table is the 1/2 by 1/2 table, the 1 by 1/2 table, and then the d functions for those.
So it reminds me about like all tables for sinuses and cosines, for sines and cosines. When I was in school, we were just taking a look like at the numbers. What is a sine of like 37 degrees?
Yeah, it's that these take a ton of work to calculate by hand, so it's a very useful table. But yeah, that's what keeps blowing my mind about this Riemann sphere ideas, because it's literally just, you know, a projection. Like, you don't have to do all this crazy solving differential equations and combining angular momenta and stuff. It just geometry.
Yeah, it wasn't really obvious for me, like if talking about that picture. So what we are doing here is that we have that OB, right? And OB is our like direction in space, our current state. Uh, and we have another state like OA, and we have a theta angle between those two states. So, and we are calculating the probability to go from B to A, right? And we project B on our like OA vector, uh, having that point C here, and afterwards we are we calculating probability as dividing A, that tick with a tick, like so we taking the opposite point for some reason, and we calculating the A tick C divided by AA here. And I was thinking then if we had like OA here, that I've been thinking that we should like divide CO by AO, for example. So it's somehow like counterintuitive for me. Why are we dividing those two? Maybe Joe, you can explain that. Like, so why we are taking AA tick length?
Well, this is a great question, because I have a very similar confusion here. I think that A prime is the measurement axis for like your Stern-Gerlach apparatus, and then OB is just the direction of the spin, um, in general. And then when we actually make a measurement using the Stern-Gerlach apparatus, it corresponds to projecting along this line A prime. But I have a similar concern, because like if the projection is just purely along A, like say B is the same point as A, then our A prime C, it seems like it would give a lower or a smaller result, whereas we should actually have like a full projection onto A. That should be 1. But if we're dividing by A prime, it'll always be less than 1.
But like if your point C will go to the A, we will have 1.
So then theta would be 0.
Yeah. So we will actually have 1. Yeah. So maybe it's like connected uh, with uh, is that like spin opposite structure in terms of spherical geometry, that you always have your basis along the diameter of a sphere, like point A corresponding to plus direction and A tick corresponding to minus direction. And yeah, I think that maybe what confuses us here is that usually we are thinking about basis as something orthogonal, instead of being opposite, as in that case. And it seems that we have a little bit different geometry here, where we need to consider like the whole length of those things. Yeah, but I don't know like the correct answer for the question currently. Why? Maybe that's actually connected with the thing you said, like about the measuring those things with Stern-Gerlach apparatus. Like we have the whole AA thick lengths along which we can measure those.
Yeah, I'd be interested in seeing how this would work for like spin 1 or spin 3 halves or something. Because in the 1/2 case, our full space is 2-dimensional, right? It's either up or down. So this makes sense that you would have antipodal points. But for the like 3/2,
But I think that it will be pretty similar. So you will have that Majorana description, and you can have that like decomposition of higher spin tensor into those different Majorana directions on the sphere, and you can take a look at these similar pictures for different Majorana directions, I think. And if you will have like two different n spin states, you will have like different uh, Majorana descriptions for those, and at that point my mind wanted to draw something actually, so I just will try to think more. So for example, like for one spin state we will have two Majorana directions, and for two such particles we will have like four directions, right? And therefore I think that we will need somehow to project every one of those between themselves. Yeah, but
so
I do not know how to deconstruct those back, to sum up everything we will project.
so this is where it gets kind of weird for me, because like this list of basis vectors for the Majorana basis, it almost seems kind of straightforward in terms of the that table that I posted in the beta chat, because like see the first two spins are up, right? And let's say that they're all spin half. Each component of this cat is a spin half. Well, that was like that first table that we looked at, where both of the spins are up, right? And so these first two spins are up. That corresponds to like a spin 1 particle having a spin up, right? And then, so now what you would do is you'd go down to the 1 by 1/2 table, right? Because now we have like a spin 1 state for our first two components of this Majorana basis. And then you want to add a third component. So this is like 1 by 1/2. So now this is like a 3/2 by 3/2 state. And then now you want to add in an extra one. Well, now we look at the table on the right, we have a 3/2 state, and we want to add another 1/2, right? So you can keep building these up. And that'll give you the Majorana basis in terms of this this original spin basis or the total spin basis. So yeah, this is what's really interesting to me is like I can see where it comes from in the table, like no problem, but actually putting it in terms of the geometry, I don't like, what is the dimension of this Riemann sphere for n/2 spin?
It's the same actually. So it's just a regular Riemannian sphere, just the regular one.
And so now it's different directions would be the different spins?
Yeah, so we will have different directions, yeah, and those directions will correspond to spin 1/2 things in that decomposition.
I see. So this is, perhaps I was thinking incorrectly on the previous picture where A prime was the measurement axis for the Stern-Gerlach apparatus. I think maybe that's the wrong intuition here then.
Yeah, so here we have the definite phrase that the physical interpretation of those Majorana directions or states, that they are the direction for which Stern-Gerlach measurement has probability 0 to find the spin to be entirely in the opposite direction. In the opposite. So basically, if we measure this particle along that direction using this apparatus, then that we will have like non-zero m value or something.
So I think maybe we could find this in that same table. Look for all the zero components in the table. Are any of these coefficients 0? Oh, I see one in the 2 by 1 table.
2 by 1. Yeah, we have here 1, 0.
Because these coefficients are like the square root of the probabilities. So if it has 0 probability to end up in the opposite state, I think we're looking for zeros in this coefficient table.
Mm-hmm.
Well, apologies. I don't mean to detract too much from here, but yeah, it's just I'm having trouble making sense of the geometry.
Yeah, but that's really interesting theme to discuss. Yeah. I think that I will try to find something on that for the next time. Or maybe just like share some article with you. Okay, so yeah, and the two last subsections. So in the next one we've been talking about relativistic angular momentum, and that to like move to a more general theory of it, we need to reintroduce basically like 4-vector PA and MAB tensor from relativity. And MAB tensor was representing the angular momentum conservation and also the move around the mass center of a system, that conservation theme. Okay, and together those will give a rise to the Lie algebra of the entire Poincare group of the symmetries for the space-time, which is not abelian, and they will be just the generators of it, which has this form described here. Yeah, and we talked about the complete commuting set of operators, Casimir operators here, and that we need to construct that in the relativity case also for PA and MAB components. And to do that, we need to introduce thing which is called Pauli-Lubansky spin vector, which is actually the Hodge dual of M wedged with P here. And in tensor notation, it looks like that, using that Levi-Civita symbol added here at the front. Yeah, and by using that, we can construct two Casimir operators. One is PA multiplied by PA, basically constructed together, and another one is that spin vector contracted with itself also. And to complete that set, we need also to mix their P1, P2, and P3 operators, and for example, one component for the spin vector like S3. And there are different other choices possible here, but that choice will be important for us, especially in the next subchapters. So Penrose want to kind of fix that up here. Yeah, and basically you can see that we could have something really similar to that in non-relativistic case, where we can obtain CCS by adding E as a Casimir element together with P1, P2, J squared, and L3 operators for the angular momentum things. Yeah, and he just finished off here saying that for having those Casimir operators like to work out nicely, we need to assume that we have non-zero rest mass for the particles. So mu doesn't equal 0 here. And if it equals 0, we will need to use the other formula for the spin vector, uh, which will depend on the helicity here and will just be multiple of the PA vector. And for that case, we will have smaller independent commuting set of operators here, which will be just S, P1, P2, and P3. And it turns out that for the theory of zero rest mass particles, we will need to use twistor theory or something like that. Yeah, so let's discuss also the next subchapter. And the next subchapter was about like the general isolated quantum object. And by the quantum object here, we mean something like an atom or molecule. And there are no external forces, it remains localized, but there could be some internal forces. And because of that, we can kind of divide parameters described in such system into two classes, internal and external ones. And external parameters are actually those like PA and MAB tensor. And internal parameters will always be the relative ones, referring to the parts of the system, like angles between particles, between different parts, distances between them, etc., etc. So because of that relative nature of those, relative nature basically, they will form or will not change under global symmetries of the Poincare group. So basically we will have, if we have some kind of observable Q for that internal parameter, it will commute with global symmetry S here. So if we will act with a symmetry on our wave function and measure afterwards, it will be the same if we measure and then act with the symmetry. So symmetry doesn't affect our measurements, global symmetry. And therefore we can kind of separate the wave function into the two parts corresponding to the internal and external parameters. And usually we suppose that system is in the eigenstate of the appropriate complete set of the external parameters. So for the external parameters, we will have CCS here and corresponding eigenstates. So usually the reference frame is chosen that 3 momentum is 0, so we are kind of not moving in space, and energy is given some definite eigenvalue. So system has some definite energy here. And we can also, if you worry about the angular momentum, give those some like eigenstates, some definite eigenstates for G squared and L3 if desired. And if we go to the internal parameters, then those internal parameters will depend on the details of particular system, but usually we can think about those as small oscillators. So basically they will oscillate around some equilibrium point, as we have seen that in the chapter 20. And by using that theory, we know that we will have the normal frequencies arising from the omega squared eigenvalues of our W matrix, which could be obtained from the Taylor expansion of the Hamiltonian. And in the quantum mechanical case, we will use the Planck formula to get the energy levels for those normal modes, and they will be equal to that h bar omega. And for the higher values, we can anticipate those to have the higher harmonics, and the energy levels therefore will be like 0, h omega, 2h omega, etc., just the multiples. But that's almost the true. Almost the truth here. And actually in quantum mechanics we should also add 0 point energy to those, which equals to 1/2 h bar omega, and it comes from the theory of one-dimensional quantum mechanical oscillator. So the correct energy levels are like those, and for each mode, for each normal mode of those parameters separately, there is an energy contribution from one of these values for each eigenvalue omega of the matrix W. And for general systems, those are approximations only, because sometimes higher order terms start to play out a more prominent role, and therefore we cannot use that like theory and W matrix with PQ, which equals PQ from the Hamiltonian Taylor expansion. So we will need more powerful theory for the oscillations there. But anyway, even quantum field theory of photons or any other kinds of bosons can be treated as though the entire system is a collection of oscillators when particles are in stationary state and there are no interactions between them. And afterwards, Penrose talks about hydrogen atom. So if we have the hydrogen atom, we can think of it as a nuclei and an electron orbiting it. But in the quantum mechanical case, we won't just have the one orbit, but a superposition of different possible orbits instead, which are solutions to the Schrödinger equation. And in the most general theory of hydrogen atom, energy eigenvalues will determine the J and M values for the angular momentum and vice versa. And historically, the first theory of the atom was the Bohr's theory, and orbits there were the classical ones, and allowed energy and angular momentum were calculated from those classical orbits, plus the quantum condition was added that angular momentum should be an integral multiple of the H constant. And those orbits quantized were called orbitals. And that process worked out really well, but was unsupported by the later theory of quantum mechanics, which gave more accurate results and allowed to simulate, usually only numerically, the behavior of more complicated atoms and molecules. And Penrose also talks about the energy states for atoms, that usually atoms are found in nature in what is called the ground state, like the lowest energy state for the atom, and more energetic states are called excited states, and atoms tend to emit photons to get back to the lower energy states, to stay like closer to the ground one. And the frequency of single photon emitted is calculated by the Planck's formula here, and energy difference is just the difference between the two states. And actually, I'm recalling like when I was finishing my school, we were doing those things, but I like never was able to imagine what we are doing actually. So it was kind of mechanical things to do. And like 10 years or like maybe even 15 years afterwards, after the school material, I'm sitting here and reading the underlying theory. So it's pretty fascinating that people are trying to like put that information to the child minds actually. So it's kind of pretty hard to wrap around even now, while reading that theory. And anyway, those frequencies are tightly connected to what is called the spectral lines for the different atoms, and actually those spectroscopy things are used to determine, for example, chemical nature or like chemical compounds for the stars in astronomy. And for you can see on the picture here that different atoms will have different like absorption spectrum and emission spectrum. So basically that will kind of determine the like the kind of the material or stuff the object is composed of. Basically we can just it's like a fingerprints for the atomic material basically. So like different like helium or I don't know hydrogen will have different absorption emission spectrums there, and we kind of can detect those by getting the light from the stars or something. Basically that electromagnetic spectrum from the stars. And quantum mechanics nicely can explain those using the theory of ground and excited states. And also it answers the question why the electron doesn't fall in the nuclei, because we have like a minimum energy state which just doesn't allow it to fall. on something, and we just cannot kind of go further through it. I also added a link here where you can read more about that thing. Yeah, and the final point made in this chapter was that the discreteness of quantum numbers like J and M for the angular momentum is due to the compactness of some space in consideration. And that's actually where the quantum things are rooted, and you kind of need to take into account the compactness of the spaces used in the theory, because that's where the discreteness arises. Yeah, so that's it. Any questions about those two subchapters?
I have one comment. I just came to home and I was listening to this last part, and this is very much related to the gamma ray investigation. I was doing this in the last week. So can we deal with this subject a little bit?
With what?
So this chapter about the quantum nature of the photons and such. So I was thinking if you know any sources that have made experiments with a different electromagnetic spectrum than photons, than the visible photons or X-rays. Have you ever seen any experiments?
Yeah.
With X-rays and gamma rays?
I only heard about those from you, actually, from that link you sent to the beta channel.
Okay. How about Joe? Because you are doing the high energy physics. Did you already take?
Well, so your question is about what experiments are being done using gamma rays?
Yes. Well, exactly what I'm thinking is if people have made the double slit and the beam splitting experiments with all the spectrum and ranges from the visible light down to the gamma ray spectrum. If they have tried to make those like particles, trying to make the particles coming from the lower state of the spectrum.
Yeah, and gamma ray is just like more energetic photon, basically, yeah?
Yeah, so...
Yeah, I think so.
The problem is that those have a smaller wavelength, so like I guess the actually engineering the slit to be the right distance apart might be hard, but they've definitely done it with the lower energy.
Yeah, like the
photons.
molecules even.
Well, that's a great that's a great example. Is that it's hard to actually design a slit that's on this size because the gamma rays are just so small. You can see they're like picometer wavelengths. So in order to do like a double slit experiment, you'd need slits that are a picometer wide and a femtometer apart. So it's very hard to engineer anything like that. And then even then, if you don't want to do like a double slit, you want to do like a beam splitter, like a half silvered mirror kind of thing. Well, the issue with that is the issue with that is that gamma rays, they penetrate a lot deeper. It's called the skin effect for materials. So like materials have this this physical property called the skin depth, and that's kind of dependent on the conductivity of the material and the polarizability of it. And it's just hard to actually manufacture a beam splitter for gamma rays because the skin depth is so deep. Like, gamma rays are like for example, they had to block off Chernobyl like 3 times, right? You block it off, and the gamma rays are still penetrating through this. So you build another wall around it, 2 meters of lead, and it's still penetrating. And it's like, these things, they penetrate so deeply that you can't actually do like a beam splitting experiment with it, so far as I know.
Okay, yeah. This was one consideration in the discussions with Eric and other people. So
to answer your original question,
if gamma ray can be reflected.
Yeah, to answer your original question of like what experiments are being done with gamma rays, well, I think the closest thing that to what you're asking about is the Mossbauer effect. And so the Mossbauer effect is where you have like 2 radioactive nuclei, and one of them undergoes a gamma decay. And yeah, so here it is. So one of the particles undergoes a gamma decay, and then the other actually absorbs the gamma ray and ends up in an excited state. And so they can actually measure the recoil of the particle that absorbed the gamma ray, and from that recoil you can get like interesting information about the. I think it's mostly a special relativity experiment where you're trying to figure out how the recoil of the absorbing particle ends up affecting the ultimate like energy level. Yeah, so they say here energy is lost to the recoil. So it's like you have a gamma ray coming, but like when it absorbs it, it recoils, and so it actually absorbs a lower energy photon than what was emitted. I think this is closest to the sort of experiment you're asking about.
What does it mean to recoil?
That's nice.
Well, so if I throw a cannonball at you and you catch it,
Mm-hmm.
you'll be thrown back because of the momentum of the cannonball. So that's the recoil.
Uh-huh.
I mean, another case is like, a rocket. It propels itself by like throwing mass away from it,
Mm-hmm. Mm-hmm.
right? And the propulsion is a recoil from throwing that mass.
Mm-hmm. Okay, thanks. Uh-huh.
So I think it's that the emitting particle, when it emits the photon, it's like the rocket throwing out some mass. So it ends up Doppler shifting the photon because now there's like relative motion. And so that energy loss due to the recoil can give you some. I'm not exactly sure what exactly they're even measuring here, but I think it's just the Doppler effect at high energies. I think that's what they're studying in this.
So the current view of the quantum nature of the electromagnetic waves is that the quanta nature should go from radio scale to the light and the X-rays to the gamma rays. So the quantum nature should be like be there on every scales. Is this right? So the quantum nature, it means that the electromagnetic waves are emitted in particles, in certain size of particles, having certain energy. So what I'm asking, just a confirmation that there shouldn't be different regions in the spectrum that are behaving a little bit different.
I think so. I'm not too sure I understand the question fully, but I will try to answer something about that. And it's that if you have a photon with a definite frequency, it has no definite position. It's spread out over all space, right? This is like if you picture it as a wave, then a wave with a definite frequency has no definite position. This is kind of a statement of the uncertainty principle. Is that sort of what you're getting at? About like how higher energy photons would be more or less localized?
No, it's related. Yes, I'm thinking how those are. Can they be thought really and still like quanta, like we are thinking about photons?
Yeah, I think so. But it's I think it's that quanta are not necessarily bowling balls, right? The quanta are like quanta of energy, and it doesn't mean that it's necessarily localized. What it means is that when it's absorbed, there's a specific value of the energy that is absorbed. And so this Mossbauer effect does try to measure this. Specifically, it's wondering what are the limits of this quantization? Can the Doppler effect screw up this quantum nature of it? I don't know too much about Mossbauer, but the little that I do know is that it's like a one nucleus emits a gamma ray and recoils because it emits that, and then the gamma ray is Doppler shifted from that. So when it's absorbed by another particle, it's slightly lower energy, and it's not high enough energy to excite that new particle up to the next state. So even though it was exactly the energy that was required to go from the high state to the low state, at the absorption side, it's not enough energy to go from the low state to the high state. So that would be the relation between like quantum and whether or not the energy is actually conserved there. But it seems that it is, because the recoil gives you this relative motion, which gives you a Doppler shift, which gives you a difference in energy. But the whole system energy, when you include the recoil of the particle, that is conserved.
Okay. Yeah, I think when I talk about quanta, I was referring with that term to the particle nature of the source. But with Eric, he has the third kind of experiment. It's a little bit different than the beam splitting and double slit, but it should be anyway identical to those. So he has two different detectors that are placed one after other. It's a thin detector and then a thick detector, and it should produce the same result than the other two experiments. But according to his experiments, the results are different with gamma rays, and that's really looking for if it's something fundamental and interesting. Oh, there's a proposed gamma ray laser.
Yeah, but the answer says that we are still too far away from it.
Mm-hmm.
It was like 6 years ago, but anyway.
They have some good ideas for making gamma ray lasers as of recent. The idea is I wouldn't know what to call it actually, but the trick is like you accelerate a beam of particles, and they're incident on some crystal. But the crystal, rather than being like a cubic lattice or something like that, it's actually sort of a hemispherical lattice where, so you have some incident beam of particles, and they're actually sent along a circular trajectory. But your beam is charged, so when you have a collection of charged particles moving around a circular trajectory, that actually creates Bremsstrahlung, which is like the emission of photons, and that energy of the Bremsstrahlung is dependent on the radius of that spherical trajectory. So usually they create these spherical trajectories, circular trajectories using like magnetic fields, but eventually you run out of like current to run your magnet. So the trick it's consistently scattering through, and it creates this circular trajectory. And so you can make it a much tighter circle. And I think they've been successful in creating an X-ray laser from this method, and they're attempting, see matrix crystal alignment there. I haven't heard of the Borman effect, but that might be it.
One more thing I want to point out one more question, because there was at the final subsection of this session there was this mentioned, and the ground state and the excited state of the atom. The Eric claim is that the often the experiments are made, they suppose that there is only the zero state and then jump to the excited state, like from ground to the top state, and nothing between there. And his claim is that's incorrect, that there is a preloaded state of energy. And when the gamma ray wave goes to the target, it kind of loads this energy up to the threshold, and after this threshold, the quanta of energy is emitted. So have you countered or heard anything about this preloaded and loaded model? It is also called accumulation theory, and it was talked in quantum mechanics in the early years, but after a few 10 years it was forgotten and left out.
Yeah, I haven't heard much about this, because it seems that if that were the case, then we would need some other explanation as to why it only happens at high energy, right? Because if this were truly a quantum mechanical effect, photons are photons, independent of frequency. So if we would see this at the higher energies, then it's likely that we would see these sort of continuous spectra rather than the discrete absorption spectra that we see.
I got an impression that the explanation is on a Compton effect, that the energy of with gamma rays, and to get the effect, the preloaded state effect, you need to have more energy than in quantum effect. So there's one one diagram that I saw that's quite explains why it works with the higher energy. I'm not sure if you have seen that.
I still have to look at some of the sources that you sent me on this experiment.
Yeah, I can point out that picture on a little bit later on the chat when I get onto my computer. But thanks for the input anyway.
Yeah, no problem.
It's interesting that, like, as far as I recall, in your links, Mesocosmos, that guy was claiming that he has done something like that with gamma rays, something like a double slit, or no?
Yes, he has done that with two detectors that are placed very near to each other. Mm-hmm. It's a thin detector and thick detector.
It just like a bit suspicious because like we have googled a bit today and I haven't seen any like proofs that something like that could be done actually. So the best thing I was able to find is this X-rays and two adjacent iridium atoms experiment done 2 years ago.
Yeah, so I think it's not really common knowledge.
Yeah, but
probably very unique test environment.
Yeah. It just like I'm just asking myself a question, like if he was able to do that, why like he didn't manage to make that how to say that to spread in the scientific world, you know? Because it sounds like a sensation.
Yeah, that's a great question.
Like being able to do that on such a small scale.
Yeah, that's true. That's why I'm also questioning the whole thing.
Mm-hmm.
Yeah, but I don't know.
Yeah.
So I put a homepage where the